Hey there, nice to see everyone. Let's talk today about probably the main formula of the rocket science. Well, it's about the final velocity or the final speed which rocket could achieve using the reaction type of propulsion. Okay, in this type of propulsion, a certain amount of gases, okay, is thrown away from the rocket with a certain velocity u in this picture. Okay, let's call the amount of the mass of these gases as delta m. Okay, then the mass of the rocket, initial mass, let's say initial mass of the rocket is m, and with this kind of blast of certain amount of mass or mass of gases, rocket achieves the addition of velocity delta v. Okay, so we could say that by the law of conservation of momentum, m times delta v equals u times delta m. And this could be okay in case we think of delta m as of just some mass of gases, disregardless of where did they come from. Point is that delta m is connected to m, okay, to the mass of the rocket itself, and this is a part of the rocket mass. That's why velocity increases, left hand side of the equation, okay, it's plus, but the mass of the rocket decreases, so this delta m, if we think of it as of mass of the rocket, it's minus. So to make this equation true, using delta m as the decrease of the mass of the rocket, okay, we should slightly adjust it, okay? So u times delta m should be negative. Well then, okay. Now let's come to the differentials. Tiny kind of micro moments of time when this kind of process occurs. Mass of gases is pushed away to the back of the rocket, and the rocket receives some propulsion and some increase of the velocity. Let's call the kind of teeny weeny amount of delta v and delta m differentials, okay? M dv would equal negative u dm. Well then, our task in this problem is to figure out what kind of velocity could rocket achieve and what kind of mass of fuel does it need. That's what we're talking today about, okay? Well, let's slightly again adjust this equation and say, since we need to find the velocity, dv, okay, it's negative u times dm over m. And then from here on, let's take integral of both parts, okay? And we'll have integral of dv on the left hand side equals negative, u is a constant, so it could be factored out, integral of dm over m. We'll talk about definite integral because we know the initial mass of the rocket and the final mass of the rocket. Let's consider the initial speed be equal to 0 here, okay, and the final speed is just v, the achieved speed. Then let's say that initial mass was m initial sub e and then m final sub f. Basically, you see here we have the names William Moore and Konstantin Tsiolkovsky, who developed this formula in Britain and in Russia. Moore was the first. He did it in the beginning of 19th century, and Tsiolkovsky did it in the end of 19th century. and published his work, if I'm correct, in the beginning of 20th century. Well, integrating this stuff on the left hand side, we'll receive, simply speaking, v, the achieved velocity. Then negative u. This integral basically is a log, okay, natural log. So we could say this is natural log of m, okay, and it's counted from the initial mass to the final mass, like this. Let's adjust it, and then we get ln of the final mass, which is less than the initial because fuel is being burned, yeah, and minus ln of the initial mass. But since we have negative in front of the parentheses, we could just change the signs and we'll get something like this: u times ln, and I'll change them, okay? Mass initial goes first, mass final goes second, okay? Something like this. Well then, now we have plus here, see? And finally, we just use the properties of logs, and then it would be the ratio of mi and mf under the log, okay? So the final formula, which we are looking for, is like this. Is this one. V equals u times ln m initial over m final. This is probably the main formula of the rocket science. Other formulas are kind of adjustments of this formula to the gravity field, motion in the gravity field. But in any case, this formula allows us to figure out the kind of utmost possible velocity is we use the reaction gases and then the reaction motion. And thus we could see the limits we do have with this kind of propulsion, this kind of type of propulsion. Let me take it into a frame because it's pretty important, okay, like this. And let's make one more adjustment. This is the log form, but there's also an exponential form, since we could rewrite it like v over u is ln this and that. If I do it very briefly on the left, okay, like this. V over u is ln is log base e, right? me, then mf. Then we should say that basically e to the power v over u is the ratio of these masses. So the initial mass over the final mass would be e to the power v over u. Okay? Let me rewrite it here. So the initial mass over final mass is e, the Euler's number, to the power v over u. And then bring it downward, oops, like this. And take it also into a frame. This is again quite important formula. The first one allows to calculate the final velocity if we have the certain amount of ratio mi over mf, and the second allows us to kind of dreaming about the achieved velocity to calculate the needed ratio of mass initial and mass final. Let's try doing that in the next videos, okay? This will be pretty fun, but one of the limitations we kind of encountered while developing the rocket science, it was in the beginning of the 20th century, is that the kind of one-stage, so-called one-stage rocket, okay, could not achieve the needed velocity to orbit the Earth. Simply couldn't. With the chemical fuels, which were kind of accessible, it was, simply speaking, unachievable. That's why the idea was invented, how to overcome this obstacle, okay? So what do you know about this stuff? Please leave in the comments. I'll be happy to read. And next time we'll talk about it, okay? And calculate some of the cases. With this, I would like to finalize, okay? I'm pretty happy to see you here watching these videos and being interested in this stuff. Thank you for curiosity and have a nice week. Please be successful in all kinds of your studies, okay? See you and bye.